All right, let's move on to sections 3.2 and 3.4, or through 3.4. Again, the reason why I'm showing all of this at once instead of actually taking the notes is just because it's primarily writing. So I don't want for you to have to wait as I write all of the words out, because it's pretty straightforward here. It's not a lot of calculation process or methods. All right, so let me zoom in a little bit. We're going to talk about picturing distributions of data. Again, as we have done so far, we're going to split it up between qualitative data and quantitative. Remember, qualitative data, we're talking about categories. So we don't want anything with any type of numerical value. And as I go through these, know that some of these can also be used for quantitative, just as some of the quantitative can be used for qualitative. But we are talking about how they are primarily pictured. So we, although can see other types of data in different types of graphs, primarily we'll see them in these categories. So in the qualitative data, let's talk about the bar graph. The bar graph you've seen before. Here we're using bars to represent the frequency or the relative frequency of each category. And it could be done horizontal or vertical. The most important thing is, since we're working with qualitative data, our bars are separate categories here. So they do not touch at all. If we were talking colors, for example, we could have red, blue, green, but there is no connection between those categories. Similarly, with a dot plot, it is just another way to illustrate a bar graph, except instead of having bars represent the frequency, like in a bar graph, we have dots that are representing the frequency. So notice we can still depict a general shape of the stat plot, but each of our separate categories, again, do not touch. The dots are evenly spaced out, and we can see that it is just essentially a bar graph, but with dots. A Pareto chart is a bar graph, but it's going to be a bar graph that is in decreasing order. So we're going to have our highest frequency down to our lowest. Since we're using qualitative data here, we also want to make sure that we're using nominal data. Remember, with nominal, it's just a name or a category. So if we're talking about, again, color of cars, we could say white, green, blue, black, for example. There is not a natural order. If we were to use ordinal data, it wouldn't really make sense, right? So let's say that we were working with ordinal. And ordinal, for example, would be how somebody rated a movie. We could say bad, fair, good, right? It wouldn't make sense over here for us to say, oh, well, this was good, this was bad, and this was fair. Just because it's not in the natural order that we would expect that ordinal data to be in. But with nominal, it's okay. And lastly, in qualitative, we could see a pie chart. Pie charts we've seen before, especially in that announcement that I sent out with Rick Astley. Hopefully you watched the video. I did laugh as I did it. Please don't make me feel old here. Hopefully you've heard that before. But with a pie chart, we're gonna show relative frequency most of the time. So we're gonna have percentages in these wedges. Again, if we're talking car color, this could be red, 20%, for example. And the wedges are representing the relative frequency. So if it's 20% red cars, then we want 20% of that circle to be represented. Altogether, just as our relative frequencies do, we want those percentages to match or to equal 100%. I will not have you construct pie charts. I will just more have you interpret them. So just make sure that we're understanding the basic foundations of them. We can't have more than 100%. We need to have them labeled. The sizes should be appropriate. But I'm not going to take off any points where it's, let's say I have you construct one and then I say, oh, no, this looks like 21% instead of 20%. That's not my primary goal here. So don't focus too much on getting it down to be exact. Focus more on how they are constructed and how to read them. Let's move on to quantitative data. Again, quantitative data has a number value or a numerical value. With a histogram, it's going to be very similar to a bar graph, except we're going to be working with binned data. So just imagine that we're working with the binned frequency distributions that we talked about in section 3.1. So where one category ends is going to be right where the next one starts. And that is why they do touch, because it does matter where each bar begins, right? It's not like this one over here where they're separate categories. Now they go in specific bin or class size increments. We also can use for quantitative data a line graph. And so here we would have a dot in the middle of the category or in the middle of each bin. And then we're going to connect those dots with straight lines. Please make sure that we do lines here and not curves. It is very, very important that we specify which one we're doing. As we move on, we do more with curves. So here for a line graph, it does have to be lines that are being formed, straight lines connecting those dots. Let me clear this screen. Time series graph. It could be a histogram or a line graph. It doesn't matter. The main thing is that we're looking at change over time. And then with stem and leaf plots, these are one of my favorite things in statistics, and I'm not really sure why. I just think that they're so much fun. We will do more of a stem plot in an example, but what happens here is we are separating digits into stems and into leaves. Need to cross my T there. So the stem is going to be every digit that's in that number or in that data value besides the last digit. And the leaf is the last digit. So for example, if we're looking at this stem and leaf plot here, we can see that we have a stem of 22 and then 3 leaves, a leaf of 0, another leaf of 0, and a leaf of 1. Our key tells us that if we have this stem and this leaf, that's going to equal the number 220. So it could be 220 feet, 220 miles per hour, whatever it is that we're talking about. We have our stem and then our leaf. The key does only need to talk about one possible data value. It does not have to be for every single value in there. So here for this stem and leaf plot, just having this key representing this one data value is okay. Let's move down to graphics in the media. This one was a little bit harder to give examples for, so please make sure that you look at the examples that are given in the book for section 3.3. But we're going to talk about other graphs that we've seen. And most of the time, these are ones that we see in media. So they're not as often found in like statistical studies, but they are ones that we need to be comfortable interpreting. So we could see multiple bar or multiple line graphs, and it's going to be very similar to a normal bar or normal line. The only difference is instead of just having one category here in this, drawing, instead of just having one category for each data value, we can have more than one. So For example, if this was our normal bar graph, here we're looking at 2 or more sets of bars. So right next to that, we're going to have some other value. So if we're talking color of cars and how they differ amongst genders, maybe one of these would be red, and one of these would be blue, and then we can say, well, this, in our study, this is the number of boys that had a red car, and this is the number of girls. So we're looking at 2 different sets of data. And the same thing would occur if we had a line graph. It would, let me scroll up here. So essentially, this was our line graph right here. If we're looking at this line graph, let's say that this was the number of red cars sold in a certain amount of time span or at a certain location. And then we can have other data right on top of it. We're talking about those same time values or the same locations or same whatever we're measuring here, but we're just looking at 2 different data sets measuring the same thing, which is a line graph with another line graph. Maps and contour maps, we're going to show geographical data. So we'll see some examples in the reading. 3D graphs, most of the time it's very visually appealing, but it doesn't really offer anything, right? So it could make it a little bit more confusing to interpret the data. It's just not really necessary, even though it's kind of fancy. And we'll see a couple of those as well. And lastly here, talking about infographics. So this is going to be where we're using multiple chunks of information on one presentation. So we might have, you see this in sports quite a bit too, but we might have like a player sheet here, and then we have one chunk of information over here about maybe this player's baseball stats. We have another piece of information right here, maybe about where he grew up. We might have another piece over here, and it just talks about some other information. More information here, more information here, right? And so it's all information that has to do with the same thing, but it's presented very visually and with quite a few different graphics all on one presentation. Moving down to 3.4, we're going to talk about a few things that we need to make sure to pay attention to in graphics that we're looking at. And I will have more examples shown in the discussion. I link bad graphs for you. So hopefully you got some entertainment out of that, but they're very, very easily created and easily misinterpreted sometimes. One thing we need to look at is perceptual distortion. So if we see an image or a pictograph, which we talk about over here, but if we see an image, a lot of times our brain automatically sees area as representing change, even though that may not be the intent. So it's important to actually read the information that's being provided with the graphic versus just looking at an image and seeing how it's changing in size. And that also goes with pictographs. So it's misconstrued with pictures or embellishments. With amount change and percentage change, we need to make sure that we're looking at the scales of a graph. So it might look like something is decreasing, but the value may not actually be decreasing. It might just be less of an increase. So it's important to always look at what's happening as far as our scaling on the left. And so these two are connected, amount change, percent change, and scaling. So we need to make sure that we are distributing our scales appropriately Most of the time it's important to start at 0, unless our data is really far away from 0, in which case we need to consider our different intervals of spacing there. But we will see more examples of bad graphics as we go along. Just because this one is going a little bit longer than I thought, I'll go ahead and stop it here and then do a separate one for practice.